In today's lesson, we're going to be working on independent and dependent events and then also conditional probability. So when we're working on independent events, two events, A and B, are independent if the occurrence of one does not affect the chance of the other to occur. So what that means is if I have a drawer full of socks and I am picking a sock out, if I pick out one sock and I figure out what color it is, what the probability of it is, whatever the case is, and then I pick out a secondary sock, those are not independent because what I have left has now changed. Okay, I don't have all of the socks anymore. I don't have the same number of colors anymore. But if I were to pick out a sock, take a look at it, put the sock back in, pick out another sock randomly, because that's what we do, those would be independent events because the second sock being pulled out has no effect on it based on what the first sock was. Okay, so if they do not affect each other, that is called independent events. If they do affect each other, they are then dependent events because the outcome of the second one depends on what happened with the first one. So when we do two different types of probabilities, like if I'm rolling a die and picking a card, those are independent events. There's no overlap between them. But if I pick out a card, keep it, pick out another card, those are dependent events because the probability of the second one depends on what I picked the first one. Does that make sense? Therefore, if they are independent, then the probability of their intersection is just the probability of A times the probability of B. So this is a formula that we're going to work with. What it ends up being is if I want to know what the probability of the two things are, the probability of picking a two of diamonds and the probability of flipping a head, I just take the individual probabilities, multiply them together. That's an and statement. This happens and then this happens. That's why it's an intersection. Both of those things have to happen. Now, if I was going to look at a Venn diagram, I have to be careful again with that overlap piece to it. But only if they're independent can we use this premise. In your formula packet, this is that fourth one that's listed, which is independent events. Again, in order to use that formula, they have to be independent. They have to be independent. Okay, so here's our fun example that we love to do with probability. We have a bag that contains 3 red balls and 2 white ones. Another bag contains 1 red and 4 white. A ball is selected randomly from each bag. Find the probability that both are red. So again, they're 2 different sets that we're looking at. So we have a one bag that has, 3 red, 2 white. And then we have another bag that has 1 red and 4 white. So we want to look at having both of these situations. We can just look at each of the individual probabilities. So in the first bag, there are 3 red out of the total, which was 5, times the other bag has 1 red out of the 5. We just multiply these two probabilities. So therefore, 3 times 1 is 3, 5 times 5 is 25. So that was only the one situation. In example B, they're different colors. So when we pick one out of the one, we want to pick a different color out of the other bag. So we have to look at 2 different situations because there are 2 different colors. So in the first bag, if we want to pick a red, there's 3 out of the 5. But then out of the second bag, I don't want a red. Instead, I want white. So that's 4 out of the 5. Or I could pick out of the first bag a white one, so that's 2 out of the 5, times, so since I picked a white in the first one, in the second bag I have to pick a red, which is 1 out of 5. So either this first situation happens or the second situation happens. Since there is an or between them, we add the 2 individual probabilities. So if this happens or this happens, that's when we add the situations. So first we multiply this to find the probability of this scenario, which is 12 25ths, plus we multiply here, we get 2 25ths. Therefore, we get a total of 14 25ths. Part C says at least one is white. So if at least one is white, that means out of the first bag I get a white and the second bag I get a red. Or the first one I get a red and the second one I get a white. Or the first one I get a white and the second one I get a white. So there are 3 different situations where at least one is white. Or what could I do? So the option is you can do all 3 sets of probability where you get 1 white in the first, 1 white in the second, or both of them white. Or the flip of that, the complement to that would be getting 2 red and then subtracting it from 1. Because when I add up every single situation, I have to get 1. I have to get some kind of success. So take 1 minus the probability of getting 2 red, which we already did here in part A. That was 3/25. And if you did all 3 of them individually, added them all up, you should get the same answer as we got, which is 22/25. We're going to have a lot of different situations eventually, especially come chapter 14. We're going to have like 10 scenarios. So instead of adding up all 9 of them that we don't, or that we want, what we can do is just find the one that we don't want and subtract it from 1, or subtract it from 100% if we're doing percentages. So complements come in really handy. So in this investigation, we have a diagram showing the 100 students from the previous section. So in the last section, we worked with this. The diagram represents the number of students who study art and biology. If we know that a particular student studies biology, how does this affect the probability that they also study art? So what we're going to be looking at is our controls are going to change. Okay, so instead of looking at the entire population of 100 students, what we're going to end up doing is we're going to restrict it down to just part of them. And then within that group, we're going to look at what happens. Okay, so instead of looking at every single student, we're looking at a specific focus. So in order to do this, I want you guys to go through this investigation. So take a minute and work through investigation number 7 on this page. So when we look at the Venn diagram, how many are in B? What total is in B? 40, good. That's the whole B piece right here. There's 40 students within there. Of those 40 students, how many also study art? 12 does. What do we represent 12 with? What do we call this? The intersection. Good. So that's the probability of A intersecting with B. So therefore, what is the probability that a student studies art given that they study biology? So what is that fraction? 12 out of what? Say it one more time. Yes, 12 out of 40. We've restricted down our group of students. We're no longer looking at all 100 of them. We are now strictly looking at the students who study biology. That's where this given statement comes in. What is the probability that a student studies art given that they study biology? We have changed our control group. So what is the probability that a student does art given that they study biology? Given this formula. So this is how we write that. The probability of A given B. That's what this notation is. Probability of A given B equals. So this 12, what does the 12 represent? The 12 people that study both, which is the intersection. And what goes in the bottom? The probability of what? Where's the 40? B. When we do this type of problem, we ignore everything else. We don't want any of this. This is gone. This is gone. So all we're looking at is this grouping. It's the intersection, which is 12, over the whole. And this works with probability and numbers both. So to find this, we're looking at the probability of the top over the probability of the bottom, or even the number in the top over the number in the bottom. Okay, so that's what we worked with. We did the number piece. Okay, but since it was out of 100, we could have just done 0.28 and 0.12, that sort of thing. Okay, now, probability of A given B is known as conditional probability. We say the probability of A given B. So for 2 events, A and B, the probability of A occurring, given that B has occurred. That's what it's saying. We have to look at, we want to know how could A happen provided B had to happen. Okay, so B happened. This happened already. What is the probability of this happening since that happened? So that's what conditional probability does. Usually, you will be given the word given, but not always. Sometimes it is implied. Most of the time, you will see the word given, and that's telling you that it's a conditional probability. But every so often, it won't use that word given, and it's a little harder to see that it's conditional. Okay, and you're going to see an example of that here in just a second. So again, this works no matter what. The second part here, that B, is the part that's on the bottom. That's the probability of it happening. The top is the intersection. The top is the intersection. If two events are independent, that means they don't intersect at all. They don't intersect. So therefore, the probability of A given B is just the probability of A. Okay, because B has zero control over A. Just like the probability of B given A, if they're independent, is just the probability of B. Probability of A given the complement of B, because we'll see complements in here as well, is just again the probability of A. If they are independent, the given statement has zero effect on it, as long as they're independent. So this example is going to get us into that situation. So what I want you guys to do first and foremost is make a Venn diagram for the examples. Before you even answer any of the questions, please make a Venn diagram for that. Okay, so 56 teachers like to drink coffee, 37 teachers like to drink coffee. Oh, I just said that wrong. 56 like to drink tea, 37 like to drink coffee, and 12 drink neither tea nor coffee. So 12 is outside. So therefore, I had 84 teachers to begin with. So therefore, I have 72 left over for inside here. And then since 56 of them drink tea, that's between the tea and the overlap, that tells me that 16 of them must like coffee. Only coffee, only coffee. But there are 37 that like coffee, so therefore that leaves me with 21 in my overlap. Do you guys agree with that? So therefore 35 like tea when I take 56 and subtract 21. Then I add all those up, I should get up to my total number of 84 teachers. Okay, so that's just filling out the Venn diagram. Now we can answer questions quickly from it. How many teachers drink both tea and coffee? 21. 21. When one member of the teaching staff is chosen at random, find the probability that she drinks tea but not coffee. So she drinks tea but not coffee. So the probability that she drinks tea and not coffee, so drinks tea, not coffee, is how much? 35 over what? Actually over 84. It's still out of the total. This isn't a conditional yet. So 35 out of the 84 is the probability that she drinks tea and not coffee. If she is a tea drinker, this is conditional probability. So if she is a tea drinker, so that means I can only look at this group of teachers. She drinks coffee as well. Coffee as well is the intersection. That's the conditional probability. Therefore, it is 21 out of 56. In terms of notation for part C here, this would be the probability of coffee given P. So probability of C given P. So based off of that, why don't you just take a moment and go ahead and answer D on your own before I do it for you. Okay, so if she is a tea drinker, again, our restriction on the bottom is that fact that she's a tea drinker, but now it says she does not drink coffee. She does not drink coffee. So therefore, within here, the fact that she does not drink coffee, that's this half moon piece. That's the half moon. So therefore, we have 35 out of 56. This probability statement would be the probability of the complement of C in given P. Okay, so homework then. Oop, it's not that. Do not delete that.